And so let's showcase this once again with our smokers. Let's pretend, who smokes? So we can use it with someone who smokes maybe. And yeah, no one wants to admit it, I guess. All right, so you're about my eye level, so I'm going to work with you. And so we're both going to take a drag. So take your drag. And so what's happening is we're both breathing in. And so we both are creating a high pressure inside our body. And when we blow out, we're going to blow in each other's face. What's going to happen is a low pressure will form in between us. And guess what? When that air converges, you're going to see it. If I could smoke in here, I would do this. Trust me. We could show, what will happen is the low pressure, and we'll see rising. We'll see converging air, but it'll also rise. A good way to showcase how two high pressures can create a low pressure. So two high pressures, you and me, create a low pressure in the middle. I don't know if that worked or not, but since we don't smoke, it probably didn't work. And so let's go see this actual in reality. And so this is before this year. Actually, this map came out in early 2012. I mean, I would have to get out my PowerPoint and come up with one hell of a way to showcase wind moving in the United States. You see a low pressure. What's that? By Dallas. You see that low pressure just to the north and to the west of Dallas. You know it's a low pressure because that spiraling is going inward. It's also counterclockwise. And so just by looking at this wind map, this is from March 22nd, 2012, you can clearly see that low pressure. You can clearly see that low pressure that's right here. Once again, counterclockwise. Counterclockwise. And so there's a low pressure. Whereas here might be an example of a high pressure. It's a little harder to see, but we've got a great example. Let's go to today. Once again, we should see a high pressure here, right? And we do. See, is that divergence? Is that separation? You bet your bottom dollar there is. And so much of this area right here is influenced by a high pressure. Where is the center of that high pressure? Much of the West Coast is dominated by a high pressure throughout many parts of the year. And we can kind of see that. There's less winds. We see a lot of divergence. We don't see a lot of white on that in that area. So here you might say there's the low pressure is up here. The center of that low pressure is up there. And so this is all counterclockwise. And so if this map would include Canada, if it included Canada, then we could see the low pressure right through there, that counterclockwise. Now we're going to come back here later and explain what this sucker is here. And so we can already kind of visualize this. We've got air coming from the south. That air coming from the south, is it going to be cold or is it going to be warm? It's going to be warm. It's closer to the equator. So anytime we have a southern breeze, which once again, let me step back. When in geography or whatever, in weather, whatever, when we refer to wind, we refer to it as its direction it's coming from. So a western wind is coming from the west and heading to the east. Or that way, since the east is that way. So a westerly wind comes from the west, but it's heading to the east. So we've got these four individual pressure areas. And we're going to start off with the equatorial low pressure. So the equatorial low pressure, why is it green? Why do you think I colored it green? A whole lot more greenery. So that's where the Amazon rainforest is. That's where the rainforest of Southeast Asia is. That's where the rainforest of Africa is. It's all right here along the equator. And that makes sense. It's got all that water vapor. Kermit, what's Kermit's famous line? Kermit the Frog. It ain't easy being green. And that's the same way with vegetation. Vegetation requires a ton of precipitation, a ton of sunlight. So that sunlight comes from the fact that, once again, gets 2.5 times the amount of solar energy. But also, it ain't easy being green. For all that vegetation, for the Amazon rainforest to have what it has, all that dense rainforest, obviously the name rainforest, requires a ton of precipitation that we find in this area, from that predominant low pressure that exists over this area. All right, and so we should be able to see, I hope, this equatorial low pressure. One of the characteristics of the equatorial low pressure, if we go back once again, notice these arrows. What would we say as far as the direction these arrows are going from the wind perspective? They're easterly winds. They're coming from the east and they're going to the west. East, I'm shaky. East to west. And so this is an easterly wind. Do you see that here? You see that. And so we can all see convergence a bit, but you can definitely see that eastern flow. You can see how all this water vapor is moving, for the most part, in this general direction. What are we looking at once again? If we step back, this is United States right here. This is Central America. This is South America. Right here is the Andes Mountains. Over here, China, Middle East, Africa, Europe's over here, and then Russia, Siberia, and of course the poles on both ends, just to help us out as far as what we're looking at. So we zoom in, and you can see that easterly but also converging air. And so those arrows, they're not clean, I realize that, but nonetheless it's a useful model for depicting, for the most part, what happens in this area of the world. Equatorial low pressure trough, which we can see here. Once again, one of the things that I also mentioned is the equatorial low pressure trough is also referred to as the intertropical convergence zone. Convergence, once again, another dead giveaway that's indicating a low pressure. Convergence, low pressure. And so one of the things you notice is this predominant line, where is it? This predominant line of storms. You can kind of see that, right? You all see this line that's pretty much around here the entire time. There goes a hurricane, by the way. And so here we can see this equatorial low pressure, this area of high amount of water vapor, this area of high amount of storm activity. You can see that. What time of year do you think this is? What do you notice about the pattern? Essentially what we got is the migrations, moving back and forth. And so it's moving seasonally. And so one of the things you notice is as the subsolar point, when it's summertime, our summertime, what happens is the subsolar point moves closer to us here. And you can also see how the ITCZ, that rain belt, that precipitation belt, also migrates to closer to us, closer there to the Tropic of Cancer, Tropic of Capricorn. Let's pause it. And so this perfect clean line right through here. Notice how this perfect clean line, that's low pressure, that's precipitation. So that's illustrating water vapor and rain. If you notice, right now I paused it on March. March is what? The equinox or the solstice? Equinox. And so that ICC, that dense rain belt, should be right there along the equator. Is it? Sure is. So let's go down to our other seasons. Let's go to June. Now notice where it is in June. Now it's above where it is the equator. And so that makes sense. As the subsolar point moves, so does this equatorial low pressure. It moves too. So that plays a key role going forward, why some places can have one part of the year where they get a huge amount of rain. It's because the subsolar point has moved over, that equatorial low pressure has moved over their area. But then they have another time of the year where it's super dry. What happens is the equatorial low pressure has moved, and a subtropical high pressure, which we're getting ready to talk about, has now come and dominated the area. The white stuff on this map, that's a great indication of a high pressure. The absence of precipitation, absence of rain. And so we can see where I'm going to next, the subtropical high pressure, clearly on both sides of that equatorial low pressure, that ITCZ, that dense rain belt. And so here's another way to showcase this with a visualization and how this relates to what we're going to talk about in the future when we talk about vegetation. And so we can see the ITCZ. We can see as it migrates, what does it do to Africa? Essentially, creates life and vitality in an area that has a very, very dry winter period. All of a sudden, when the ITCZ moves over, all of a sudden they get a dense amount of rain. So that's one of the characteristics of a climate type I'm going to talk about in a few lectures called the tropical savanna. It has a very wet period and a very dry period. And you can see how that migrates throughout the year. Of course, I wish I could slow it down, but I probably could. But the idea here is you can see how that switches and moves throughout time. All that stuff I was talking about, subsolar point, there's a reason why I was mentioning, because it builds and builds and builds, and we can see that here. All right, moving now out to the subtropical high pressure, which we cleanly saw right here. We cleanly saw this right here. This is a great example, the subtropical high pressure. Now, once again, land and islands kind of mess with things. But if we had no land, these lines would be perfect as far as being able to show what I'm showing here. But once again, land gets in the way and screws everything up. And so the subtropical high pressure, you can see it there, you can see it there, you can see it there. Where's that subtropical high pressure also, where we also find it? What's right there? The Kalahari Desert. What's right there? The Sahara Desert. So the deserts of the world are predominant underneath this subtropical high pressure, which is around the entire year. And so that makes sense. high pressure, dry, what we see today, why these places have hardly any vegetation. Because once again, it ain't easy being green. So what we got here is we got these, once again, the two highs create the low. So here a high creates this low pressure. So as I blow in, I've already done that demonstration. We don't need to do it again. So what these arrows here, the ones that flow into the equatorial low pressure trough, are called the trade winds. So these red arrows here illustrate the trade winds. Why they call the trade winds is because if you can kind of think about, Europe here, Africa here, United States here, what they would do is they would essentially ride these wind patterns, these predominant wind patterns, these trade winds from the northeast to the southwest. And what they would do is they would come from Europe. And where are most of the African slaves, the African Americans, where are most of them from? What part of Africa? West, east, south, central, north? Overwhelmingly west. Overwhelmingly west. That makes sense because it's pretty much the trade winds scooted right along the west coast. And then using the trade winds, the African slave movement was heavily influenced. And we can see, of course, where they end up, Brazil, Caribbean, and the southeast United States. Of course, getting back was a little different. They essentially would ride those ways back to the motherland back in Europe. And so that's why they're called the trade winds. These here, once again, what direction are the arrows moving towards? They're moving towards the east. They're coming from the west. And so these are the westerlies. The westerlies are overwhelmingly important for understanding Indiana weather. There's a reason why on our weather maps, when whoever it is that's doing the weather is looking out in the Great Plains as far as what's going to be coming to Indiana. Because the westerlies bring west to east, which is overwhelmingly the pattern we find here in the United States. We are overwhelmingly in the mid-latitudes. We don't see Maryland, West Virginia at all in our weather maps. It's always Oklahoma, Kansas, Nebraska, Minnesota, all those states there. So let's see if we can see separation. Let's see if we can see in this area in which the water vapor is going in opposite directions. Do we see that? You can see the wind going this way, but then here it's going that way. You can kind of see that. Here it's east. Here it's west. You can see how these suckers are moving for the most part west to east. And so this is a westerly direction. Like I said, I wish it was clean like this. But nonetheless, why I'm doing this is I hope you can visualize these patterns, this separation that's found here along the subtropical high pressure. And once again, two highs create a low. And so while the trade winds come together to form this low pressure, the westerlies coming out of the high pressure come colliding with the polar high pressure, the other high pressure, to create this low pressure area right through here. And so we should expect, in the mid-latitude, should I expect to see a lot of counterclockwise circles or clockwise circles? Clockwise or counterclockwise? Low pressure, counterclockwise. We're in a low pressure area. So we should see, in this next image, we should see spirals that are going counterclockwise. This is an area of low pressure, in which you have these low pressures that dominate. We should see that. Once again, this is where we are. Do we see these spirals? Boom, counterclockwise, counterclockwise. West to east, exactly, counterclockwise, low pressures. So these low pressures, that's a high pressure there. See, that's clockwise. And so here we can see a high pressure dipping down, creating this, and that's coming from the polar area. So we can see that, but there's low pressure, boom. We start all over again. So there's that low pressure again. So you can see this area in which they have these spirals. These spirals are, once again, because of the direction they're spinning, they're examples of low pressures. We know that. We can see that here, I hope, very clearly. Then we have the polar high pressure. The polar high pressure, as the name implies, high pressure, dry. Why in the heck does Antarctica have a massive ice sheet that's like hundreds of feet thick? It's one of the driest places in the world. Why does it have all that ice? It's so stinking cold here that it gets a trace amount of precipitation. that trace amount of precipitation, i.e. snow, it's not going to melt. It's not going to go anywhere. And so it's thousands of years of a very minimal amount of precipitation accumulating over time to create all that white stuff that we see there in Greenland and Antarctica. And so, in fact, the driest place on Earth is Antarctica. It's not the Sahara. It's not the Gobi Desert or wherever the hell that is in Japan. The Taklamakan, or not Japan, China, the Taklamakan Desert. Big difference, right? And so the polar high pressure. So this is going to be cold, dry, dense, heavy air that because it's cold, dense, heavy, it's going to sink. And so it's going to sink and diverge at the surface. And so once again, we should see, in this case, a easterly pattern. See, east to west. So we should see an easterly pattern. And we kind of do up there, kind of, sort of. We do down here as well. It's a little harder to see because no water vapor. Once again, that makes sense. And so here it's a little harder to see this movement because of the lack of water vapor there. Does that make sense? And so we have a general pattern here in December and January. And like I said, all this migrates. It's not perfectly clean, but we can see how this corresponds to where we have dark, dark green, once again, Kermit, lighter green, where they have that one period where a bunch of rain gets dumped, but then it has a drier period, so it's not going to be as dense green, and of course, the world's deserts. Why is Africa perfect for seeing this? Africa, for the most part, has no mountains. As we'll see in a future lecture, mountains also do a good job of screwing up all these patterns as they block a lot of the flow. And so because Africa really doesn't have any mountain barriers, it's very linear. We can see this pattern very clearly where it's wettest there, not as wet, and super dry on both sides. In fact, right there, that part of South Africa is the only place in which they have seasons in Africa, and a little bit up there too, up in the northern part. And then there's highland areas that kind of get some funky stuff as well. And so all this, like I said, it migrates back and forth. So it goes back and forth throughout the years, throughout the seasons. And so this is, I guess, another way to showcase some of the things we're talking about, another visualization I have. So we can kind of see that eastward movement here. We can see this dense line of storms that are right through here along the equatorial low pressure trough. We can see the spirals. We can, just by looking at which direction they're spinning, we can be able to identify if they're a low pressure or high pressure. And so that one, let's see here, that one's spinning. Notice what direction it's spinning? Counterclockwise. And so that's a low pressure, low pressure, low pressure,